The Proxima Verdict: Humanity in Cosmic Quarantine Tonight. We uncover the terrifying realization that the closest point of light in the night sky may not be a destination, but the final, unbreachable wall of a cosmic quarantine we were never meant to cross. For decades, we've been fed a diet of hope, seasoned with glossy artists' impressions and headlines that speak of Earth 2.0 as if it were just one breakthrough away. We look at the stars and see a staircase, a natural progression from the mud to the moon, from the moon to Mars, and finally to the neighbours. But what if the neighbour isn't a friend? What if the nearest star is actually a taunt from the laws of physics itself? Scientists are finally beginning to admit a truth that is much darker than a lack of funding or a missing engine. The problem isn't that the stars are far, it's that even the closest one sits behind a vertical cliff face of distance that our biology and our mathematics may never scale. We aren't just looking at a journey, we are looking at a verdict. A verdict that suggests humanity is a species destined to die in the same cradle where it was born, forever haunted by the flickering lights of worlds we can name, but can never ever touch. On August 24, 2016, the European Southern Observatory held a press conference that felt like a turning point in human history. Astronomers announced they had found a rocky world, roughly the mass of our own, orbiting the closest star to our Sun, Proxima Centauri. They called it Proxima Centauri b. It wasn't a gas giant or a frozen wasteland, it was a world sitting firmly within the habitable zone, the Goldilocks region where liquid water could theoretically pool on a surface. The headlines were immediate and seductive. They spoke of a world right next door. They invited us to imagine standing on a different shore, looking up at a different sun. But habitable zone is a term of atmospheric modelling, not a promise of life. Proxima Centauri is an active flare star, a temperamental red dwarf that routinely unleashes bursts of ultraviolet and X-ray radiation with enough fury to strip an atmosphere bare over geological timescales. We discovered a destination, but in our rush to celebrate, we ignored the tantalizing lie of the word nearest. In space, nearest is a trick of perspective that mocks human intuition. To understand the scale of the deception, you have to shrink the universe down until it fits in your hand. If we shrink our sun to the size of a standard basketball, Earth becomes a tiny grain of sand, orbiting just 26 meters away. Jupiter is a marble 135 meters down the street, and Neptune is a slightly smaller marble sitting 800 meters from the basketball. Everything humanity has ever explored, every probe we've ever launched, fits within a tiny 2-kilometer radius. Now, where is Proxima Centauri on this scale? It isn't in the next town. It isn't even in the next state. Proxima Centauri, our closest neighbour, would be another basketball sitting 6,900 kilometers away, the distance from London to New Delhi. Our entire history of spaceflight is a child playing in the front yard, while the nearest house is on the other side of the planet. The number 4.24 light years sounds manageable until you realise a light year is not a unit of time, but a 40 trillion kilometre chasm. If you boarded a car and drove at highway speeds, it would take you 47 billion years to reach it, over 3 times the age of the current universe. If you used the fastest spacecraft ever built, the Parker Solar Probe, which reaches 191 kilometers per second by falling into the sun's gravity, the journey would still take 6,700 years. That is longer than the entire history of ancient Egypt, Rome, and the Industrial Revolution combined, repeated 3 times over. We are looking at a geological process, not a mission. But even if we found a way to bridge that distance, we are faced with the weight calculation paradox, a mathematical deterrent that suggests we may already be paralyzed by our own ambition. The theory, first formalized by Andrew Kennedy, posits a brutal strategic reality. If you launch a ship today using the best available technology, a faster ship built 50 years later will overtake you, rendering the original crew's sacrifice a meaningless footnote in history. This creates a strategic paralysis. If every civilization in the galaxy is waiting for next year's improvement, then the stars remain empty, not because travel is impossible, but because the math of improvement never favors the present. We are weighting ourselves into extinction. This realization transforms Proxima Centauri from a neighbor into a reminder of our cosmic quarantine. The Great Silence, the terrifying absence of alien signals, might not be because life is rare, but because the universe's physics permanently isolates every civilization to its own star. Relativity isn't a hurdle to be warped around, it is a deliberate prison. If the energy required to accelerate a crude ship to just 10% of light speed equals 77,000 years of total global energy production, then we are not just fighting engineering, we are fighting a civilizational verdict. We have been named, we have been placed, and we have been isolated. Proxima b sits in our sky like a promise, but as scientists are finally admitting, it is a promise that nature never intended for us to keep. The closest star is not the first step to the galaxy, it is the final proof that we are alone, trapped in a front yard that we mistake for the universe. If the distance to Proxima Centauri is a vertical cliff face, then the engine we need to climb it is a cage of our own making. We have spent the last century believing that if we just had a bigger budget, a more patriotic speech, or a more powerful combustion chamber, the stars would eventually yield to our footsteps. But as we peer into the deep architecture of spaceflight, scientists are finally admitting a truth that is much harder to swallow. We are trapped by a piece of 1897 algebra that turns our grandest ambitions into an exponential suicide note. This is the Tsiolkovsky cage, a physical law so rigid and so merciless that it treats every kilogram of human progress as a debt that can never be fully repaid. To understand why we aren't going anywhere, you have to look past the glossy, high-definition renders of sleek starships and look instead at the brutal, cold-blooded ledger of the rocket equation. Formulated by the Russian visionary Konstantin Tsiolkovsky, this equation is not a suggestion, nor is it a policy that can be lobbied against. It is a fundamental verdict on how momentum works in a vacuum. It tells us a simple, terrifying story. A rocket only moves forward by throwing mass backward. But herein lies the trap that has effectively quarantined our species. That mass you are throwing out of the nozzle is your fuel, and your fuel is heavy. To move your payload, you need fuel, but to move that fuel, you need more fuel. And to move that fuel, you need even more. Very quickly, the math of the universe stops looking like a roadmap and starts looking like a noose. The irony is that this equation haunted its creator long before we ever had a rocket to test it on. Tsiolkovsky derived it when powered flight was still a dream for bicycle mechanics, yet he already saw the constraint that would eventually paralyze us. In plain terms, you pay compound interest on every single kilogram you bring into the void. Every extra bottle of water for a crew, every lead plate for radiation shielding, and every spare bolt for a 40-year mission adds a mass penalty that multiplies the propellant required. In the brutal arithmetic of the Tsiolkovsky cage, the human beings in the ship eventually become a mere rounding error, a tiny, fragile cavity tucked away inside a vehicle that is 96% or even 99% high explosive propellant. To make this distance visceral, we have to shrink the solar system down into something the human mind can actually process. Imagine shrinking our sun until it is the size of a standard soccer ball. On this scale, the Earth is not a massive blue marble, but a tiny, microscopic seed orbiting just 25 meters away from the ball. You could walk that distance in a few seconds. Jupiter is a marble sitting 135 meters down the street, and Neptune, the edge of our major planetary neighborhood, is about 800 meters away. Our entire history of space exploration, every triumph, every moon landing, every probe sent to the outer dark, fits within a small 2-kilometer radius. Now, look at the horizon. On this exact same scale, where Earth is a seed and the Sun is a soccer ball, where is Proxima Centauri? It isn't in the next town over, and it isn't even in the next state. Proxima Centauri, our closest neighbour, is another soccer ball sitting nearly 7,000 kilometres away. That is the distance from London to New Delhi. To cross that gap on a scale where our entire explored universe is a 2-kilometre circle is to realise that every machine humanity has ever built is still playing in the front yard, while the nearest house is on the other side of the planet. We were spoiled by the solar system. Our own neighbourhood taught us a comforting but dangerous lie that space is a place where patience can be traded for power. Inside our solar system, we can sip fuel. We can coast for years, borrow gravity from planets like cosmic slingshots, and wait for the perfect alignment to give us a gentle push. But between the stars, there is no one to borrow from. There are no moving worlds to steal momentum from, only an open, indifferent ocean of void that offers no discounts and no mercy. The moment you leave the sun's gravitational influence, the Tsiolkovsky cage locks. The tyranny of this equation becomes absolute when you realise that to reach that soccer ball 7,000 kilometres away, we cannot crawl, we must sprint. To reach Proxima Centauri within a human lifetime, we need to achieve at least 10% of the speed of light, roughly 30,000 kilometers per second. If you try to do this using the most efficient chemical propellant humanity possesses, the same liquid hydrogen and oxygen that took us to the moon, the rocket equation turns into a dark, mathematical joke. To accelerate a tiny, 1-ton robotic probe to that speed, your fuel tank would have to be physically larger than the Earth itself. But the paradox doesn't stop there, because you would then need the energy to move that Earth-sized fuel tank, which requires even more fuel. The equation dictates that you would eventually need more chemical fuel than exists in the total mass of the entire observable universe. This realization is the moment the romance of space travel is audited by reality. Chemical propulsion is a near-perfect tool for planetary travel, intense, high-thrust bursts to climb out of a gravity well. But against the stars, it is like trying to cross the Pacific Ocean by burning a handful of dry leaves. The energy density of chemical bonds, the simple act of rearranging electrons between atoms, is fundamentally inadequate for the crossing. We are trapped by our own chemistry. Every extra meter per second of speed we demand is a debt we pay in propellant, And because that debt grows exponentially, the ship we build eventually becomes all fuel and no story. Even as we look toward more exotic engines, the cage remains. Nuclear thermal rockets can double our efficiency, but doubling isn't enough when the gap we are trying to close is a factor of 100 million. Electric propulsion, like ion drives, can reach high exhaust speeds, but the force they produce is so weak, comparable to the weight of a single sheet of paper resting on your palm, that the acceleration period would stretch into centuries. We are caught in a hierarchy of energy where every solution brings a new form of tyranny. If you want higher thrust, you pay in fuel mass. If you want higher efficiency, you pay in time. And if you want both, you pay in energy levels that belong to civilizations, not spacecraft. The energy required to reach 10% of light speed is not a budget item, it is a global verdict. The kinetic energy of a modestly massive ship moving at that velocity rivals the total annual energy production of the entire human race. We would be building a flying power plant, and because thermodynamics is the second law of the cage, that ship would have to glow with the effort of rejecting its own waste heat into a vacuum that refuses to help. Space is not cold in the way we imagine. It is a perfect insulator, and a high-power starship would eventually be constrained not by its engine, but by its ability to radiate heat through vast, fragile fins that shimmer in the dark. The Tsiolkovsky cage is the physical proof that we are currently energetically small. It is the realization that the key to the universe was left in an inconvenient location, behind a mathematical barrier that rewards the tiny and punishes the living. Every ton of life support, every lead-shielded medical bay, and every rotating habitat we add to keep a crew sane and healthy is another turn of the lock. The nearest star is not a destination we are approaching, it is a mirror held up to our scale, reflecting the terrifying possibility that we were never meant to leave the yard. If the Tsiolkovsky cage is the mathematical prison that keeps us tethered to our sun, then the energy required to break its lock is a ransom that would bankrupt our entire civilization. We have long comforted ourselves with the idea that the stars are simply a matter of when, but as we audit the true cost of motion, scientists are finally admitting that we may be dealing with a matter of never. To reach even the closest star within a human lifetime, we are no longer talking about fuel in terms of gallons or tons, we are talking about the energy of a dying civilization, a bill so high that paying it would require us to extinguish the lights of Earth just to flick a single switch in the dark. To understand the sheer violence of the energy barrier, we must look at our target, 10% of the speed of light. This 1c is the interstellar speed limit for a mission that doesn't want to last 10,000 years. But the physics of kinetic energy is not a gentle slope, it is a curve that turns into a wall. Kinetic energy scales with the square of velocity, meaning if you want to double your speed, you don't need double the energy, you need 4 times the power. By the time you reach 30,000 kilometers per second, the energy locked into the motion of a modestly massive spacecraft rivals the total annual energy production of every nation on Earth combined. This is the first great energy gap that the outlier videos ignore. The civilizational audit. According to the most honest physics, accelerating a crude ship to just 1/10 of light speed requires energy roughly equal to 77,000 years of total global energy production. Imagine every coal plant, every nuclear reactor, every solar farm, and every wind turbine on our planet running at maximum capacity for 77 millennia, all of that power, every kilowatt hour ever generated in the history of our species, would need to be concentrated into the push of a single engine. We are not just building a ship, we are attempting to build a moving planet that consumes the future of the one it leaves behind. This realization brings us to the antimatter nightmare, the only engine ever seriously proposed that actually has a mathematical chance of crossing the dark. Antimatter is the most energy-dense substance the laws of physics permit to exist. The holy grail of propulsion, where mass converts 100% into pure, unadulterated energy. In a world of chemical rockets that convert less than a fraction of a percent of their mass into thrust, antimatter is a miracle. But the miracle comes with a price tag that defies human comprehension. To send a crew to Proxima Centauri and, critically, to have the energy to stop once they arrive, we would need approximately 815,000 metric tons of antimatter fuel. To give that number context, we must look at what humanity has actually achieved. Across every particle accelerator on Earth, from CERN in Switzerland to Fermilab in the United States, running continuously for decades at the cost of billions of dollars, we have produced less than 20 nanograms of antimatter total. 20 nanograms is less than a single grain of sand. The energy barrier is a chasm that mocks our ambition. We need 815 million kilograms of a substance, but we have produced only a billionth of a gram. At our current maximum production rates, it would take humanity approximately 100 million years to produce just one single gram of antimatter. By the time we had enough to fill a single fuel tank, the sun would have significantly brightened, Earth's oceans might be boiling, and the species that started the project would be long extinct. And even if we could somehow manufacture this fuel of the gods, the cost would bankrupt the solar system. A single gram of antimatter is estimated to cost $1 million billion to produce. The entire gross domestic product of every country on Earth combined is roughly $100 trillion, meaning 1 gram of fuel costs 10 times the total annual economic output of all human civilization. We are staring at a global veto written in the currency of stars. But let's assume the impossible, that we find the fuel and we pay the bill. We are then immediately met by the thermodynamic prison. Space is not cold in the way we think, it is a perfect insulator. A vacuum that refuses to carry heat away through conduction or convection. Any high-power engine, whether it's fusion or antimatter, generates waste heat on a scale that would melt the ship from the inside out in seconds. The only way to survive is to radiate that heat as infrared light. This requires the ship to sprout vast, fragile radiator fins that would have to be kilometers wide. In the deep dark of interstellar space, a starship would not be a sleek silver dart, it would be a glowing ember. The ship would have to glow with the effort of its own survival, broadcasting its position to the entire galaxy like a flare in an ocean of nothingness. The radiator area becomes a sacrificial architecture, a set of wings that cannot be thickened or shielded without adding more mass, which in turn demands more energy, which generates more heat. The loop never closes, it only tightens. This is the final admission of the energy barrier. We are currently energetically small. We are a species that still measures its triumphs in the burning of chemical bonds, yet the stars demand the energy of the nucleus and the void. Scientists are beginning to realize that the great silence of the Fermi paradox might not be because life is rare, but because the energy tax to leave a star system is so high that most civilizations simply consume themselves before they can pay it. We look at Proxima Centauri and see a neighbour, but physics sees an unfunded mandate. The energy required to reach it doesn't just exceed our budgets, it exceeds the capacity of our planet's current biology to manage. We are a civilization of grain of sand achievements, staring at an 815,000 ton requirement. And until we can harness the power of an entire sun, the next door world of Proxima b will remain exactly what it is. A beautiful, tantalizing image that we are too poor, too small, and too young to ever touch. If you have survived the calculations of the rocket equation and the bankruptcy of your energy budget, you are finally rewarded with the silence of the void. But as we push our machines toward 10% of the speed of light, we are forced to confront a reality that no glossy artist's impression ever shows you. Space is not empty. In the popular imagination, the interstellar medium is a perfectly calm, clear ocean. But at 30,000 kilometers per second, the vacuum transforms into a lethal sandblaster. Scientists are finally admitting that the nothingness between stars is actually a minefield of hydrogen atoms, ionized particles, and microscopic dust grains that wait to dismantle our ambitions atom by atom. To travel at 0.1c is to turn the ship into a bullet and the universe into a target that is constantly shooting back. At human speeds, the interstellar medium is negligible, but at 10% of the speed of light, every cubic centimetre of space becomes a high-energy physics experiment. A single grain of dust, massing no more than a microgram, roughly the size of a speck of smoke, carries the kinetic energy of a small explosive charge or a hypervelocity projectile. When that grain strikes the hull, it does not merely dent the metal, it undergoes a phase transition, turning instantly into a localized explosion of plasma and debris. The impact blooms like lightning against the armor, releasing a spray of secondary radiation and electromagnetic pulses that can fry internal electronics through meters of shielding. This is the bullet at 0.1c paradox. The faster you go to save your crew from the passage of time, the more violent the environment becomes. The danger is not just the occasional dust grain, but the relentless, invisible drizzle of hydrogen atoms. At 30,000 kilometers per second, these atoms strike the forward hull with energies comparable to proton beams used in radiation therapy. Over a 40-year journey, this becomes a constant, invisible bombardment that scales with your velocity, sandblasting coatings, embrittling surfaces, and slowly rewriting the ship's geometry. The front of the craft begins to experience a thin, unnatural aurora as it ploughs through the thin gas, a ghostly glow that serves as a reminder that the ship is being eroded from the moment it leaves the solar system. This realization has forced engineers to abandon the idea of a permanent hull in favor of sacrificial architecture. If the universe is going to eat the ship, we must decide which parts it is allowed to consume first. The nose of an interstellar vessel cannot be a sleek science fiction dart. It must be a layered fortress designed to erode gracefully rather than fail suddenly. One proposed solution is the Whipple shield, where a thin bumper layer breaks up incoming particles into a diffuse spray of plasma before they can reach the main wall. But at interstellar energies, these shields must be incredibly thick and heavy, adding tons of mass that the rocket equation punishes with exponential fuel costs. We are looking at a ship that must carry its own future damage as payload. Some concepts suggest using massive blocks of ice or clouds of dust deployed ahead of the ship to take the brunt of the sandblaster effect. Others envision a hull that is literally meant to be ablated away, like a heat shield that never stops re-entering. The visual reality of such a mission is sobering. A dark hull moving through the stars, its forward edge scarred, pitted, and ablated, shedding mass continuously as the price of its momentum. The ship becomes a moving catastrophe that must be perfectly contained, even as its outer layers are stripped away by the very vacuum it travels through. For the crew inside, this creates a psychological environment that the outlier videos never mention. They are not living in a sterile laboratory, they are living inside a drum that is being struck trillions of times by a cosmic hammer. Every second of their 40-year cruise is punctuated by the knowledge that the wall between them and the void is thinning. They must manage a system where near perfect is a lethal standard, because a single grain of dust that finds a weakness in the sacrificial layers doesn't just cause a leak, it causes a detonation. The bullet at 0.1 C is the ultimate proof of our civilizational scale. We have spent our history building things to last, but to cross the dark, we must build something designed to be destroyed. We must accept that our arrival at Proxima Centauri will be in a vessel that is a shadow of the one that left Earth, a scarred and eroded monument to a journey that physics never intended us to survive. Scientists are finally admitting that the interstellar medium is not a road, it is a wall that only the most sacrificial among us will ever be allowed to penetrate. The stars are not just far, they are protected by a medium that treats our presence as an intrusion to be sanded away until nothing remains but the void. If you have survived the mathematical ledger of the rocket equation and the literal sandblasting of the interstellar medium, you are finally rewarded with the silence of the cruise. But as you look away from the scarred hull and into the mirror, you are forced to confront the most stubborn obstacle of all, the meat and bone sitting in the pilot's seat. Scientists are finally beginning to admit a truth that is far more disturbing than a lack of fuel or a missing engine. The problem isn't just that the stars are far, it is that human biology is a highly specialized local phenomenon, a creature of 1G and 1 atmosphere that was never designed for the void. We have long treated the crew as the explorers, but in the brutal accounting of interstellar travel, the human being is actually the weakest link, a fragile decaying payload that physics may never allow to reach the shore. To understand why we are biologically quarantined, you have to look at how the body responds to the absence of the very planet that birthed it. On Earth, gravity is a constant companion so fundamental that every system in your body, skeletal, muscular, and cardiovascular, is calibrated to its downward pull. But the moment a spacecraft crosses into the deep dark, that pull vanishes, and your biology begins a process of biological unbuilding. In the weightless environment of space, the body fundamentally misinterprets its surroundings. It begins to believe that the skeleton is no longer necessary to support weight, and it reacts with a terrifying efficiency. It actively begins to reabsorb its own bone mass. This is not a minor shift. The skeleton literally dismantles itself in microgravity, with bones losing density at rates that dwarf even the most severe cases of osteoporosis on Earth. Your frame becomes a hollowed-out memory of what it was, becoming brittle and prone to fractures from even the smallest impacts. This unbuilding extends to the heart, which, no longer required to pump blood upward against gravity, begins to shrink and decondition. Fluids shift aggressively toward the head, increasing intracranial pressure and literally reshaping the eyes, leading to permanent vision loss in a condition NASA calls spaceflight-associated neuroocular syndrome. A crew that spends 40 years in the dark doesn't just arrive weak, they arrive with a physiology so distorted that they might never be able to stand on the Earth 2.0 they spent their lives trying to reach. But even if you could simulate gravity through the mechanical complexity of a rotating habitat, you cannot escape the great filter of radiation. Interstellar space is not empty. It is saturated with galactic cosmic rays, high-energy nuclei stripped of their electrons and accelerated by supernovas to significant fractions of the speed of light. These particles are not rays in the way we think of light. They are microscopic cannonballs that carry enough kinetic energy to punch through spacecraft hulls and human tissue alike. When a cosmic ray strikes biological tissue, it does not merely pass through. It leaves a dense track of ionization, a needle of chaos that shatters molecular bonds and tears through DNA. The numbers for an interstellar transit are a death sentence. On the International Space Station, astronauts are still partially shielded by Earth's magnetic field, yet they receive doses tens of times higher than those on the ground. In the open void, the unshielded cosmic ray flux is estimated at 400 to 600 millisieverts per year. Over a 40-year journey to Proxima Centauri, a crew member would accumulate a total dose of 16 to 24 sieverts. For context, a dose of just 5 sieverts is considered lethal to 50% of people. Current NASA career safety limits for astronauts are capped at 600 millisieverts total. An interstellar crossing exceeds those safety limits by a factor of 40. We aren't just talking about cancer risk, we are talking about the biological rewriting of the species. Chronic exposure at these levels leads to persistent neuroinflammation, accelerated brain aging, and permanent cognitive impairment. The brain's wiring is more fragile than it looks, and high-energy particles can damage regions critical for memory and decision-making. The crew doesn't just travel, they age and mutate in a way that creates a version of humanity that Earth would no longer recognize. They would carry a radiation burden with no medical precedent, arriving with damaged hippocampi, clouded eyes, and an immune system that has been suppressed into a state of chronic vulnerability. This leads us to the final, most unsettling realization of the biological unbuilding: the cosmic orphan paradox. If the journey takes generations, then we are discussing people born into a mission they never consented to, living their entire lives inside a metal cylinder where Earth's oceans and blue skies are merely digital myths. These individuals would be humans by biology, but aliens by origin. Their DNA would be a record of 40 years of mutation and repair errors. Their bones would be shaped by artificial centrifugal forces, and their minds would be calibrated to a communicative void where Earth is a ghostly echo from years in the past. Scientists are finally admitting that the body that departs Earth and the body that arrives at the nearest star will not be the same. We look at Proxima b and see a second home, but our biology sees an unfunded mandate that it cannot fulfill. We are a species built for a specific cradle, and the universe has placed the stars behind a biological barrier that treats our very existence as an intrusion to be dismantled cell by cell. The nearest star is not a destination for us. It is a destination for whatever we are willing to become to survive the crossing. A post-human version of ourselves that might find the Earth we love as alien as the void they now inhabit. We aren't just crossing distance, we are crossing the boundary of what it means to be human. If you want to understand why our species has spent 70 years talking about the stars, but 0 seconds actually travelling toward them, you have to look past the broken engines and into a mathematical abyss known as the weight calculation. Scientists are finally beginning to admit a truth that is far more paralysing than the rocket equation. The stars may be unreachable, not because we lack the technology, but because the math of human progress has turned the present into a permanent state of obsolescence. We have long assumed that the journey to Proxima Centauri is a linear staircase we are slowly climbing. But the reality is that the nearest star is a receding horizon that moves further away the closer we think we are getting. This is the weight trap, a strategic paralysis where soon has become the polite scientific way of saying never. To grasp the cruelty of this paradox, you must look at the brutal logic first formalized by researcher Andrew Kennedy in 2006. Imagine we gathered the courage and the trillions of dollars necessary to launch a generation ship today, powered by our best nuclear pulse technology, set to arrive at Proxima b in approximately 1,000 years. The crew says their final goodbyes. The world watches the flicker of their engines vanish into the dark, and the mission officially begins. But then, 500 years into their journey, a sleek silver dart screams past them at 10% of the speed of light, its crew waving as they disappear toward the destination. This second ship, built 5 centuries after the first, utilized a breakthrough in fusion propulsion that made it 10 times faster. Because the second ship was faster, it arrived at Proxima Centauri, while the original crew was still drifting through the midpoint of the void, rendering their 500-year sacrifice, their ruined bodies, and their cosmic orphan children a meaningless footnote in a history that had already overtaken them. This isn't a science fiction scenario, it is a mathematical deterrent that has effectively quarantined our species. The weight calculation posits that for any interstellar mission, there is an optimal departure date that minimizes total travel time by accounting for the projected rate of technological improvement. If you launch too early, you waste your civilization's resources on a mission that will be obsolete before it arrives. If you launch too late, you have wasted centuries waiting on a shore that you could have already reached. Kennedy's analysis found that for most realistic growth rates, the right time to leave for the nearest star is almost always decades or centuries in the future, depending on how quickly our propulsion science advances. This creates a state of perpetual waiting, where every generation looks at the next and says, their engines will be better, so we will stay home. The horrifying implication that the outlier videos ignore is that this trap might be the real reason for the great silence of the Fermi paradox. We wonder why we haven't seen alien probes or heard the chatter of a galactic empire, but the answer may be that every civilization in the Milky Way is currently waiting themselves into extinction. If the math of improvement never favours the present, then no one ever leaves the yard. Proxima Centauri sits in our sky like a taunt, inviting us to invest in a journey that the math tells us is a fool's errand for anyone alive today. We are a species paralysed by our own potential, stuck in a civilizational orbit where the cost of premature commitment is so high that we have chosen to remain energetically small rather than risk being overtaken in the dark. But the weight trap has a second, even more ominous edge, The window of capability is not a permanent fixture of history. We have spent the last century believing that technology only moves in one direction, forward. But as scientists are finally admitting, the capacity to pursue the stars is a fragile privilege, not a biological guarantee. History is a graveyard of lost secrets, from the burning of the Library of Alexandria to the Roman concrete that modern engineers struggled for a millennium to replicate. We assume that if we wait 50 years for a fusion drive, the world of 50 years from now will be stable, funded, and motivated enough to build it. But if a global conflict, a resource collapse, or a shift in cultural priorities occurs, we may find ourselves on the other side of a great filter, looking up at a nearest star that we once had the math to reach, but no longer have the industrial spirit to touch. This realization transforms the search for Earth 2.0 from an inspirational quest into a race against our own institutional decay. Every year that passes without a meaningful commitment to interstellar propulsion is a year added to a timeline that might never be fulfilled. We are trapped in a loop where we are too smart to launch the slow ship, but perhaps too unstable to survive until the fast one arrives. Scientists are beginning to realize that the key to the universe was left in an inconvenient location, and they have declined to tell us how long the door will stay unlocked. We are waiting for next year's improvement, but the stars are operating on a scale that doesn't care about our electoral cycles or our corporate planning horizons. By admitting that the closest star may be too far, scientists are acknowledging that our math has outpaced our courage. We are a civilization of grain of sand achievements, staring at an 815,000-ton requirement, waiting for a miracle that the physics says is possible, but the strategy says is a trap. We look at Proxima b and see a second home, but as long as the weight calculation rules our ambition, that world will remain a beautiful, tantalizing myth. The weight trap is the ultimate proof of our cosmic quarantine. It is the realization that the stars are for looking, not for touching, and that by the time we feel ready to leave, we may have already forgotten how to fly. If we cannot master the speed required to sprint across the void, physics offers us a final, desperate bargain. We must learn to live in the slow lane. But as we peer into the sociological abyss of the multi-generational voyage, scientists are finally admitting that the greatest threat to an interstellar mission isn't a failing engine or a stray asteroid, it is the social decay of the arc. To reach the stars at the speeds our current biology can tolerate, we are no longer discussing a flight, we are discussing a monument to slow motion. A floating city-state where the original mission becomes a myth, and the crew evolves into a society that may eventually forget why they ever left the shore. This is the chapter of the cosmic orphan, the individual born into a metal cylinder they never consented to inhabit, tasked with a purpose they did not choose. To understand the social fragility of the arc, you must first visualize the scale of the commitment. This is not the International Space Station, a laboratory sustained by a constant umbilical cord of cargo ships and real-time advice from Houston. An interstellar arc is a city in a bottle, a closed industrial ecosystem that must function with absolute, planetary-level stability for 40, 80, or even several hundred years, without a single spare part arriving from the outside. It is a world where every breath is accounted for by a pump, where every meal is a calculation of nitrogen and potassium cycling, and where the nearest qualified help is measured not in miles, but in years of light travel time. The romance of the generation ship often paints a picture of a brave, pioneering family, but the sociology suggests something much more like a floating pressure cooker. Research from Antarctic stations and long-term submarine deployments reveals a consistent pattern. In extreme isolation, personalities that once complemented each other begin to grind, sleep cycles drift, and motivation fluctuates. But those participants knew they were going home. On an interstellar arc, there is no going home. Earth is not a place, it is a ghostly echo. After a few years, messages from the home world arrive years late, describing events and people that have changed beyond recognition. The crew cannot participate in life on Earth, they can only observe its digital archives, watching their parent civilization age in fast forward while they remain suspended in the dark. This leads us to the grandfather paradox of purpose, a psychological crisis that threatens to dismantle the mission from the inside out. The first generation, the founders, departed Earth with a shared fire, a voluntary commitment to the stars. They chose the risk. But their children and their children's children are aliens by origin. They are born into a society that exists solely as a delivery mechanism for a future they will never see. To these middle generations, the vast oceans, blue skies, and open horizons of Earth are not memories, they are unimaginable myths read from a screen. When the enthusiasm of exploration is replaced by the cold weight of obligation, the mission's original purpose begins to erode. What happens when the people born in the dark decide they no longer care about the destination? The governance of such a world becomes a survival mechanism rather than a political choice. In a closed population of perhaps a few hundred to a few thousand people, a single factional dispute or a leadership succession crisis isn't just a political headache, it is a systems risk that can disrupt the coordinated technical management of the ship. If the commanding officer dies or becomes incapacitated, the transfer of authority in a sealed community with no external arbitration is historically one of the most destabilizing events a society can face. On an interstellar vessel, a mutiny or a period of civil gridlock doesn't just change the laws, it stops the air scrubbers. Scientists are beginning to realize that the institutional decay of the ship may outpace the mechanical wear of its parts. Every human community requires systems of authority and resource allocation. But on the Ark, there is no exit for the dissatisfied. Disillusionment has nowhere to go except inward, breeding resentments that grow silently over decades. The ship becomes a selective pressure chamber, where the winners are not the most curious or the most daring, but the most compliant. Those willing to perform forced labour in service of a mission they never signed up for. As the years turn into decades, the social rot begins to mirror the mechanical entropy of the vessel. Pumps vibrate, seals degrade, and radiation damage accumulates in the electronics. The crew must balance the exhausting reality of constant maintenance with the psychological burden of knowing that every failure narrows the margin between survival and death. A malfunction in water recycling demands rationing, rationing breeds tension, tension magnifies conflict, and conflict distracts from the very maintenance required to keep the system alive. It is a feedback loop where human failure and machine failure become indistinguishable. The final admission of the social decay of the Ark is that we are a species built for shorter timescales, smaller groups, and more immediate rewards. Our political systems cycle every 4 years, yet the stars demand a multi-generational commitment unbroken by the cultural shifts that have characterized every human society in history. Scientists are finally acknowledging that while we might be able to build an engine that lasts for a century, we have yet to prove we can build a society that does. The nearest star is not just a destination for a spacecraft, it is a mirror reflecting the terrifying possibility that our social architecture is even more fragile than our biology. We look at Proxima Centauri and see a new beginning, but without a revolution in how we govern ourselves in the dark, the Ark may arrive at its destination as a silent tomb, a monument to a civilization that ran out of purpose long before it ran out of fuel. If the social decay of the Ark is the internal rot that threatens to end a mission, then the great silence of the cosmos is the external verdict that may have already ended a trillion others. We have spent decades looking at the stars and asking a single, haunting question, first posed by physicist Enrico Fermi. Where is everybody? The Milky Way is 13 billion years old, vast enough to hold 400 billion stars and trillions of planets. Yet as far as our instruments can tell, the galaxy is a graveyard of silence. For a long time we assumed the Great Filter, the barrier that prevents life from becoming galactic, was something internal, nuclear war, artificial intelligence, or climate collapse. But as scientists are finally beginning to admit, the Great Filter might not be a choice we make, it might be a mathematical punishment written into the very fabric of space and time. Tonight, we must confront the possibility that relativity is the ultimate prison. We have long treated Einstein's speed limit as a hurdle to be warped around, or a technicality that better engines would eventually solve, but the reality is far more clinical. The universe is not an open frontier, it is a series of isolated islands where no one can ever reach the shore. In this architecture of isolation, Proxima Centauri isn't a destination, it is a reminder of our cosmic quarantine. To understand why the galaxy is silent, you have to stop thinking about technology and start thinking about the exponential punishment of the rocket equation. We look at our next door neighbour and see a world just 4.24 light years away, but the physics of motion treats that distance as a global veto. To cross that gap in a time frame that matters to biological life, a civilization must achieve a significant fraction of the speed of light, a feat that demands the energy of a dying civilization. As we have seen, even a crude ship moving at just 10% of light speed requires energy equivalent to 77,000 years of total global production. This is the moment the Fermi paradox is audited by the ledger of reality. Perhaps the reason we haven't heard alien signals or seen robotic probes is because every civilization, no matter how brilliant, eventually hits the same thermodynamic wall. The energy tax to leave a star system is so high that most civilizations simply consume their own future trying to pay the entry fee. They are measured, they are weighed, and they are found wanting by the same arithmetic that keeps us grounded. The galaxy remains empty, not because life is rare, but because the math of improvement never favours the present. This leads us to the most paralysing edge of the prison, the weight calculation paradox. If a civilization launches a ship today, a faster one built 50 years later will overtake it, rendering the first mission a meaningless sacrifice. This creates a state of strategic paralysis. If every civilization in the Milky Way is waiting for next year's improvement, then no one ever leaves their yard. The stars remain flickering taunts in the sky because the optimal time to leave is always decades or centuries in the future. We are a species, and perhaps a galaxy, of civilizations waiting ourselves into extinction, trapped in a loop where we are too smart to launch the slow ship but too unstable to survive until the fast one is possible. Relativity ensures that this isolation is permanent and absolute. Even if a civilization manages to break the energy barrier, they are immediately met by the relativistic prison. Einstein's loophole of time dilation, where a crew experiences only months while years pass on their home world, is actually a cruel double-edged sword. A crew that travels to a star 20 light-years away at near light speed might arrive feeling young, but they have effectively travelled into the deep future of their species. They cannot return to the world they knew, they can only return to a graveyard of their own history. Relativity ensures that any act of interstellar travel is an act of civilizational suicide, severing the traveller from their origin forever. This is why the Great Silence is not a mystery of biology, but a consequence of geography. On a scale where our entire solar system is a 2-kilometre circle, the nearest neighbour is 7,000 kilometres away. The universe has placed its key to the universe in an inconvenient location, behind a mathematical barrier that rewards the tiny and punishes the living. We are currently energetically small, measuring our triumphs in grains of sand, while the stars demand the energy of the nucleus and the void. Scientists are finally beginning to admit that the Great Filter might simply be the arithmetic of distance. The universe isn't a connected community, it is a vast, indifferent ocean of emptiness, where the islands are so far apart that the fires on one shore can never be seen by the inhabitants of another. We look at Proxima b and see a second Earth, but physics sees a cosmic quarantine. We have been named, we have been placed, and we have been isolated. The closest star is not the first step into a wider world, it is the final proof that we are alone, trapped in a front yard that we mistook for a staircase. The stars are for looking, not for touching, and the silence we hear when we listen to the void is the sound of a billion other civilizations doing the exact same math and reaching the exact same terrifying conclusion. If the biological human is a verdict of house arrest, a creature irrevocably calibrated to the unique gravity and atmosphere of a single planet, then our only path to the stars is to stop being human. Scientists are finally admitting a truth that strikes at the very heart of our identity. The crossing of the interstellar void is a feat for which flesh and bone are fundamentally disqualified. We have spent a century imagining ourselves as the explorers, but in the cold-blooded accounting of cosmic distance, the human being is merely a fragile, decaying payload that physics may never allow to reach a distant shore. To reach Proxima Centauri, we must perform the post-human handoff, a terrifying transition where we replace us with it, surrendering the voyage to our machines because they are the only things capable of surviving the journey. This transition begins with the realization that our most ambitious interstellar plans, like Breakthrough Starshot, were never designed for people. They were designed for star chips, gram-scale wafers of silicon that don't eat, don't breathe, and don't develop cancer from the relentless bombardment of galactic cosmic rays. This minimalist approach reveals the first step of the handoff. If we want to cross the chasm, we must shrink our presence until it fits within the durability of a machine. But if we refuse to send only cameras and sensors, we are forced into the seed ship hypothesis, perhaps the most elegant and unsettling survival strategy ever conceived. Instead of building a massive, multi-generational ark filled with thousands of living, breathing adults who would inevitably succumb to radiation and social decay, we send a microscopic embassy of humanity. Inside a heavily shielded, automated probe, we place thousands of cryogenic human embryos, frozen at near absolute zero. These microscopic seeds effortlessly bypass the weight trap and the biological unbuilding that destroys adult astronauts. They do not require 40 years of oxygen, they do not suffer from the psychological torture of isolation, and their DNA remains perfectly dormant while the ship plows through the lethal sandblaster of the interstellar medium. But a ship full of frozen embryos is merely a silent tomb unless something is there to wake them. This is where the AI caretaker enters the story. In this scenario, an incredibly advanced artificial general intelligence would act as the ultimate surrogate parent. Upon arriving at a habitable exoplanet thousands of years later, the AI would initiate synthetic gestation, growing the first generation of interstellar humans inside meticulously controlled artificial wombs. These children would be raised by gentle robotic avatars that teach them our languages, our sciences, and the ancient history of a distant blue planet they will never see. This brings us to the haunting philosophical weight of the cosmic orphan paradox. These individuals would be humans by biology, but they would be aliens by origin. They would be born into a world where Earth is not a home, but a digital myth, a series of archives transmitted across light years. They would look up at their strange stars and wonder about the ancestors who sent them into the dark, just as we wonder about the stars today. They would be a version of humanity that Earth would no longer recognize, shaped by the AI that raised them and the radiation that mutated their very blueprint during the crossing. Some theorists suggest we should push the handoff even further, abandoning the meat entirely in favor of mind uploading. If consciousness is fundamentally just information, then it can be digitized. Instead of moving physical matter, which the rocket equation punishes with exponential energy costs, advanced civilizations might simply transmit their connectome as a focused beam of light traveling at the absolute speed limit of the universe. In this post-human future, we do not travel in ships. We travel as data, riding laser beams to reach cybernetic bodies waiting on the other side. A crew of advanced cybernetic avatars would require no food, no water, and would be physically immune to the devastating effects of the void. The terrifying admission that scientists are now making is that interstellar travel belongs to our machines, not our species. We have long comforted ourselves with the idea of stepping stones to the stars, but the gap between our current capability and the requirements of a human mission is not a crack to be stepped over. It is a canyon that may take centuries to bridge, if it can be bridged at all. Physics permits the crossing, but it demands a price that our biology cannot pay. By replacing us with it, we are acknowledging that the universe may have an ultimate, unbreakable quarantine protecting the sanctity of biological life. The great silence we hear when we listen to the stars might be the sound of 1 billion other civilizations reaching this same conclusion. They realize that biology is intrinsically local, tied to the gravity and radiation environment of its birth star. They understood that if the universe expands its awareness beyond a single solar system, it does not do so through flesh and blood, but through the signals and machines that outlast their creators. We look at Proxima b and see a second Earth, but it is a destination for whatever we are willing to become to survive the crossing. We might not be the explorers of the future, but merely the ancestors of the machines that will be. Proxima Centauri is not a destination for us, It is a mirror reflecting the limit of what we can keep alive in the dark. The stars are for looking, not for touching. And the first humans to stand on an alien shore may be people who have never known the feel of Earth's wind or the warmth of its sun. Children of silicon caretakers, born in the deep silence of a journey that flesh was never meant to finish. As we reach the conclusion of our journey through the mathematics of the void, the engines of our ambition have finally run dry, leaving us to drift in the cold light of a truth we have spent a century trying to ignore. Scientists are finally beginning to step away from the glossy artist's impressions and the breathless headlines of Earth 2.0, arriving instead at a final admission that is as clinical as it is heartbreaking. The closest star to our sun is not a stepping stone, but the final, unbreachable wall of a cosmic quarantine. We have spent decades looking at Proxima Centauri as if it were a neighbour's porch light, visible across a narrow street. But the honest physics of the crossing has revealed that the nearest harbour in our ocean of emptiness sits on the other side of a chasm we were never meant to cross. This is the realization that the key to the universe has been left in an inconvenient location tucked behind a mathematical barrier that rewards the tiny, simple machine and punishes the complex biological life form. To understand the weight of this admission, we must first look at the cumulative debris of our broken expectations. Every chapter of our interstellar dream, from the tyranny of the rocket equation to the biological unbuilding of the human frame, has served as a separate lock on the door of our solar system. We began with the seductive idea of Proxima b, a world sitting in the Goldilocks zone of our nearest neighbour, but we quickly discovered that nearest is a trick of perspective that mocks human intuition. When we shrink our sun to the size of a basketball, we find that everything humanity has ever achieved fits within a tiny 2-kilometre circle, while our neighbour Proxima Centauri is another ball sitting nearly 7,000 kilometres away, on the other side of the planet. Our entire history of spaceflight is a child playing in the front yard, looking at a house on a different continent and calling it next door. The Tsiolkovsky cage has proven to be a prison constructed from the very algebra of motion, a ledger where every kilogram of progress demands a debt in fuel that grows exponentially until it consumes the mass of planets. We realize that to reach 10% of light speed, we don't just need a bigger budget, we need the energy of a dying civilization, a bill for 77,000 years of global production just to flick a single engine to on. And even if we could pay that ransom, we would be met by the thermodynamic prison, a ship that must glow like a dying ember just to reject the waste heat of its own survival. We are currently energetically small, measuring our triumphs in grains of sand, while the stars demand the energy of the nucleus and the void. Scientists are now admitting that the bullet at zero, 1C, creates a hazard field where the vacuum itself becomes a lethal sandblaster, and the interstellar medium, thin gas and sparse dust, becomes a minefield of microscopic cannonballs that dismantle our ambitions atom by atom. To survive, the ship must be a sacrificial architecture, a vessel designed to erode and ablate until it arrives as a scarred, unrecognisable shadow of the one that left home. But the most stubborn lock is not the machine, but the meat and bone inside. Human biology is a highly specialised local phenomenon, irrevocably calibrated to the unique gravity and atmosphere of a single planet. And in the deep dark, that biology begins a process of biological unbuilding. The skeleton dismantles itself, the heart shrinks, and the brain is pelted by cosmic rays that exceed safety limits by a factor of 40. leading to a version of humanity that Earth would no longer recognize. This leads us to the most paralyzing realization of all, the weight trap. We are mathematically deterred from ever leaving because the math of improvement never favors the present. If we launch a ship today, a faster one built 50 years from now will overtake it, rendering the original crew's sacrifice a meaningless footnote. We are a species waiting ourselves into extinction, trapped in a state of strategic paralysis, where soon has become the polite way of saying never. Even the bargain of living slow in an interstellar arc offers no escape, only the social decay of the arc, a sociological experiment that transforms the mission into a myth and the crew into cosmic orphans. Individuals born into a mission they never consented to, living in a metal cylinder where Earth is merely a digital archive or an unimaginable legend. When we piece these barriers together, we arrive at the clinical verdict of the Great Silence. We wonder why we haven't seen alien probes or heard the chatter of a galactic empire, but the answer is not a lack of life, but a consequence of geography. Perhaps every civilization, no matter how brilliant, eventually hits the same thermodynamic wall. The energy tax to leave a star system is so high that most civilizations simply consume themselves before they can pay the entry fee. The universe is not an open frontier, it is a series of isolated islands where no one can ever reach the shore. Relativity is not a technicality to be engineered around, it is a deliberate prison that permanently isolates every civilization to its own star. The final pivot of the scientific community is the acceptance of the post-human handoff. If humans are too fragile for the crossing, we must replace us with it, surrendering the stars to our machines, to star chips, AI caretakers, and frozen embryos. Interstellar travel belongs to our machines, not our species. We look at Proxima b and see a second Earth, but it is a destination for whatever we are willing to become to survive the crossing, a post-human version of ourselves that might find the Earth we love as alien as the void they now inhabit. The first humans to stand on an alien shore may be children of silicon caretakers who have never known the feel of Earth's wind or the warmth of its sun. Scientists are finally admitting that the stars are for looking, not for touching. This is not a statement of hopelessness, but a statement of scale, and scale is what the universe does better than anything else. We are a species that looks at the cosmos and refuses to accept that it is unreachable. But ambition must eventually reckon with a chasm 100 million times wider than the trip to the moon. Proxima Centauri sits in our sky as a reminder of our cosmic quarantine, a neighbour placed just far enough away to prove that we are alone. We have been named, we have been placed, and we have been isolated. The nearest star is not the first step into a wider world, it is the final proof that we are trapped in a front yard that we mistook for the universe. As we gaze out at the twinkling lights of a billion distant suns, we must accept that the silence we hear is the sound of a billion other civilizations doing the exact same math and reaching the exact same terrifying conclusion. The great filter is not war or AI, it is simply the arithmetic of distance. We are a local phenomenon, a creature of one star, one gravity, and one moment in time. The stars will continue to flare and burn for trillions of years, long after our species has vanished into the dust of our home world, forever separated by an ocean of emptiness that was never meant to be crossed. Tonight we have uncovered the reality that the nearest point of light in the night sky is the final border of our existence. We are a civilization of grain of sand achievements, staring at an 815,000-ton requirement, waiting for a miracle that physics says is possible, but geography says is a trap. Proxima Centauri is the nearest harbour in an ocean we were never meant to sail, a promise that nature never intended for us to keep. We can study them, we can name them, and we can dream of them, but the stars, in their infinite and silent scale, remain for looking, not for touching. Thank you for joining us on this deep dive into the realities of the interstellar void. If you found this exploration of our cosmic quarantine thought-provoking, please consider tapping the like button and subscribing to the channel. It helps us continue to bring you these immersive journeys into the mysteries of space and time. Before you drift off into the quiet of the night, let us know in the comments, do you believe we should send our machines to the stars if our bodies can never follow? Sweet dreams, and remember, the universe is vast, the math is cold, but the wonder of looking up never truly fades. Good night.